Hello everyone, my name is Shambhavi. Hope you all are doing well. So now what we are going to learn we're going to learn about how to calculate out the F ratio for the two estimates of the variances are made. So I'll be writing out and we'll be going to calculate the F ratio today. That's how we can do that out. Okay. So let me write that. So here it goes to calculate. One second. Let me write that correct only. So to calculate the F ratio, to calculate out the F ratio, two estimates of the variance are made. Two estimates of the variance are made. Okay. So to calculate the F ratio, two estimates of the variances are made. Fine. Now, basically first one what we have, and before that let me choose out a new color here for writing out, and fine here, and the number one goes here like that, variance between the samples. Okay, so number one is variance between samples. Okay, the very first one which we have out here. Now we'll be discussing about some things between the variance between the samples. Okay, so yeah, here I go that an estimate of sigma square, that is the an estimate of sigma square, that is the basically variance, that is the variance of the sample, that is the variance of the sample means, that's the variance of the sample means multiplied by n, multiplied by n. Okay, so the variance between samples means that an estimate of sigma square, that is the variance of the sample means multiplied by n, right? Basically next one second, let me get out some space for writing out here. Fine. Next we have that if the samples are different sizes, if the samples are different sizes, okay, basically if the samples are different sizes, then the variance between samples is weighted, to account for the different sample sizes, for the different sample size. Let me just go ahead above a little bit and revise that particular variance between samples. So it is an estimate of sigma square, that is the variance of the sample means multiplied by n. Okay. Now, if the sample are different sizes, then the variance between samples is weighted to account for the different sample size. Right, so I hope I am very much clear with this particular thing. Then in that case, we have one more thing to mention out here, that the variance is also, one second, let me get out some space. The variance is also called variation due to treatment or explained variation. So the variance is also called variation due to treatment or the explained variation, right? So yes, this was about the variance between the samples. Now Next we are having the second one, that's the variance within the samples. Variance within samples. Now let me just come down here. Okay, fine. Variance within samples. So it is an estimate of sigma square, that is the estimate of sigma square, that is the average of the sample, variances, that is the average of the sample variances. Now when the sample size, one second, right, so when the sample size, okay, so here we are having that when the sample sizes are different, so in that particular case the variance within samples, the variance within samples are weighted. Okay, then in that case the variance is also called as, I will just write simply like variance is, let me get out some space, and in that case variance is also called as variation due to error, or unexpected variation, So in the variation within the samples, what happens that an estimate of sigma square, that is the average of the sample variances when the sample sizes are different, and the variances within the samples are weighted. So variance is also called as variation due to error or unexpected variation. Okay, so this is where this variance within samples actually meant. So these were the two estimates how you could found out the F ratio. Okay, variance between samples, and second one is variance within samples, right? So hope I am very much clear with both of these things in regarding about to how to calculate out the F ratio. Two estimates of the variances are made, right? So in this particular case above we had seen about the one, that is the variance between samples. So that was estimate of sigma square, that is the variance of the sample means multiplied by n, right? And when I move towards the variance, variance within samples, so it is an estimate of sigma square, that is the average of the sample variances, right? So hope I am very much clear with both of these things. Now we'll meet you in the next video with some more new topics. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now after studying these different types for the estimation, now I'll be taking you towards the next topic, to the further topic onto this particular only. Right, so I'm going to take out a different color here so that it separates between the previous and the new lectures. So here we go. So now I have some denotions here as well. So what we had studied, once again let me take the cursor right here. So what we have studied here, that it was variance between the samples, right? So variance between the samples, and one was variance within the samples. So whenever we just wrote this out, we write out in the form SS, and here in the denominator we write out here as between. So here it is SS and denominator is the between, right? So into that we have the sum of squares, that represents the sum of the squares that represents PRESC and TS, right? So SS between is basically the sum of the squares that represents the variation, so here goes the variation among among the different samples, So this is about this particular SS between, that the sum of the squares that represents the variation among the different samples, right? Now, this was between, and next we were having one more, that was SS within, right? That we had studied as well. So now what was that? So let's go ahead with that particular thing once here. So that was the sum of, so it was the sum of squares that represent and that represents the variation. So here we have the variation. So SS within is basically the sum of squares that represents the variation within the samples. Within the samples, let me just cut down out here and let me get out some space. Within the, right here we have. So that, okay, the sum of squares that represents the variation within the, we have here the samples, SM, yeah, right, it's okay. Samples, that is due within the samples, that is due to chance. So here goes the chance. Great. So SS within. So this is basically the sum of squares that represents the variation within the samples, and that so is basically due to chance, right? Now, what do we basically, to find out the sum of a square, what do we meant from this particular word that I was saying, that starting the sum of the squares? This one which I had used out in here as well, this particular one, right? So what does this actually means out? So this actually means that to add together squared quantities. Now, which basically in some cases may be weighted, right? In some of the cases it may be weighted. So to add together both, so add on those squared quantities together, right? This is what this particular term is. Okay, now basically why we just use out the sum of squares? So we use out the sum of squares to calculate out the sample variance, and basically for calculating out the standard deviation. Now where it is used completely, it is used in the descriptive statistics. So in the descriptive statistics, the sum of squares is used to calculate out the sample variance and to calculate out the sample standard deviation, right? So hope I am very much clear with both of these things to you, that basically what are these means and what are the things that we have out here. Now, next we are having some more things to go ahead here. So I would just start writing those things. I would just not dictate that out. So right here we go. So now we have one another term, that is MS, capital M, that capital S. Now what does that actually means? So MS means the mean square. So it's the mean, and here it is the square. Okay, so MS means the mean square. Now what is that MS between? So I would just write out that thing as well. So MS between, one second. So here it goes the between in the denominator, right? So MS between is the variance. MS between is the variance. So here goes the variance between, MS between is the variance between groups and MS within, and MS here goes the within. So MS between is the variance between groups, and MS within is the variance between the, sorry, not between, it's the variance within the, because between is almost finished up, right? Because we discussed it above. So here goes, and is MS within is the variance within the groups, right? So that was about the MS mean, that was the mean square, right? So MS between is the variance which is between the groups, and when I talk about MS within, so MS within is the variance that is within the group. So both are different things, right? So when I talk about that some variances between the groups, so that is another one. And when I talk about that some variances within the groups, so that's again a different thing, right? So this is about the MS means, that is the mean square. Let me take you to above a little bit once. Right here, 1 second. Great. So SS basically was the denotation that we used, right? We used SS between, that was the sum of the squares that represented out the variation among the different samples, right? We just did out this particular thing, that was one of the sum of the squares. So SS basically means the sum of the squares, okay? Now what do this SS between represent? So it represents out the variation among the different samples. When I talk about, except this between, when I talk about the within, so what about the within? So SS within is basically the sum of squares that represents out the variation within the samples that is due to chance. So in SS within, the sum of squares which appear out that represent out the variation within the samples, and that is due to chance. What is the meaning of MS right here? So MS means the mean square. Okay, what is the meaning of MS? MS means the mean square. So MS between is the variance between groups, and MS within is the variance within the groups, right? Yeah. So hope I am very much clear with the like definition and with the part for this both of these, that what are these SS and what are these MS, how to categorize categorize them between within and the between of both of these functions. What are these completely meant? What is the meaning of sum of squares? What is the mean of squares? And I hope all of these things are very much clear to you. Now what are we left with? Now we'll be doing out and studying out that how we do the calculation for the sum of squares and the mean square. That we will be going ahead in the next video. Right, so hope you got out all the things very clear in a very clear way regarding whatever I just told you right here. So we'll see you in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So as we already discussed about the mean of squares and sum of squares, all the things we are already familiar with, right? So now I'll be discussing about one of the very important topics today, and that is basically the calculation of sum of squares, and mean squares square. Okay, so this is what we are going to discuss up. So we'll be seeing that how we'll be doing out the calculation for the sum of squares and even for the mean of squares. So what's the procedure that we need to follow? All those things we'll be seeing up here, right? Now, I'll even be denoting out some different terms as well, so as to remember out the notations and what do they actually mean. That as well I'll be doing throughout. Okay, great. So here we have the first one, that is the k, that's the small k. So that is basically what means that out. So that is the, okay, that's not the different, it's the number. Yeah. So it is the number of different groups. It is a number of different groups, right? So this is what is the calculation of sum of squares and the mean square. So k is basically one of the terms that we are having, and it is a number of different groups, right? Now moving towards the next point, we are having n of j here. Okay, what is that? So that is the size. It is the size of the jth group. So it is the size of the jth group. So whenever you see out a notation written like n and in the denominator j, so you could understand that, okay, this is the size of the jth group, right? Now let me come down to the next third point, and now here what we have s of j. Okay, we have the next value, the very next value, that is s of j. What is that actually meaning? So that means the sum of the values. It means the sum of the values in the jth group. So when we talk about n of g, so it means the size of the jth group, okay? And when we talk about s of g, so it means the sum of the values in the jth group. Fine. Next, moving towards the number 4. So number 4, we are having small n. What is that? So that is the total number of, it is the total number of all the values total number of all the values combined. Okay, so what is the small n? Small n is basically the total number of all the values combined. Fine. So even we could just as well say out it is a total sample size, that is sigma of n of g. Okay, right. Let's come down here. Next we are having number 5th, and that's the x, small x, that is equal to one value. Okay, one value, that is sigma, and here goes the x, that is equal to sigma, and here goes s of g. Okay, yes, this is what it is used for. So x is equal to one value, sigma x is equal to sigma s of g. Fine. Next we are having about the sum of, squares, of all values, from every group combined. So yes, next we are having sum of squares of all values from every group combined, and what's that? That's sigma of, and here we go with the x square. So that's the sigma of x square, right? Now moving towards the point number 7. So next we are having that between group variability. So I will just write that as well. It's between group variability. So here goes the variability. It means what is that? It is the SS total. Okay, and what's the formula for that SS total? So the formula for that is sigma of x squared minus, we have the sigma x whole square divided by n. Okay, one sec. Okay, that's a too much mess up right here, right? So let me just go down, get out some space for me to write out. Fine. So the formula which we are having for this particular is sigma x squared, that sigma x squared minus, in the bracket we have sigma x, into the bracket above we have a square, divided by n. Yes, now this is the formula which we have for the between group variability. Okay, sigma x squared minus sigma x whole square divided by n. Okay, next we are having the number 8. So the number 8 we are having here, that is the total sum of squares. Total sum of squares, right? So onto this particular total sum of squares, so we have total sigma x square minus, we have sigma x whole square divided by n. Okay, so this is the total sum of, formula for the total sum of squares which we are having here. Then now we have the explained variation. So it goes explained variation. Now that we have a sum of squares representing REPRESCN like this, right? So sum of squares representing the variation among the different samples among the different samples, right? So that's completely the explained variation. Samples, and we could say that as SS between. SS, and downside we have like this between, and that is equal to SS between, that is equal to let me get down from here so that I could get out of some space for writing. SS between, that is equal to, I would write it out here. So its sigma bracket goes on like this. So we have, I would just write out Sj whole square divided by n of j. Bracket closed like this, subtracted. Then we have sigma s of j bracket whole square divided by n. Okay, so yeah, right. Hope you are very much clear with this particular thing as well, whatever I had just written out at this particular place. Now, fine. So explained variation already done. What about the unexplained variation? Okay, the number which I had mentioned above was number 9. Okay, right here. Okay, now it goes to number 10 here. That's the unexplained. It's the unexplained variation. Okay, it's the unexplained variation. Now, what is that actually unexplained variation? So, it is a sum of squares. It is a sum of squares. It is a sum of squares representing. It is the sum of squares represent PR. Okay, that is REP representing. Okay, it is sum of squares representing variation. Representing variation within the samples. Representing variation within samples due to chance. Okay, so unexplained variation is basically the sum of squares representing variation within the samples due to chance. So what's the value for that? So it is SS width. Sorry, it's not width, it's within. 1 second. So it is SS within is equal to SS total and minus SS between. Minus SS between. Right? So yeah, this is done. Now, right. So here we have many. We have some more things as well to be noted down. But right here, I'm just gonna stop about this particular place only for this particular video. So we had seen about the different ways for the calculation of sum of squares and the mean square. So these were the different ways that we have seen right here. Right. So hope you got out the idea very clearly regarding this particular thing, that how we will be able to do out all of these particular things. Right, so this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So we were going to the discussion of, 1 second, I will just put on the cursor right here. Right, so we were going on a discussion for the calculation of sum of squares and the mean square. Right, this was what we were doing that discussion for. So on to that, we had seen out the several parameters. I would not give you a revision of that right here. We'll be discussing that at the last. Right, first let me finish up all of those parameters, all of the steps, all of the things which we are having here. Okay, so what I'm going to do is that let me start on with the color, and let's start out with the writing of some stuffs right here. So let's take out this one and let's proceed on. So yeah, here we go with the number that's 11, right? Previously we had sorted the 11 number that was 10th. So now here what I'll be doing is that I'll be starting with the 11 number, and into that particular we are having some different means as well to go ahead. Okay, now I'll be talking about the degrees of freedom right here in the starting. So I'll be talking about the degrees of freedom, that's the DFs, right? So the DFs for the different groups, okay, like I would just discuss about the DS for the numerator. So DFs for the, and here goes the numerator. So numerator, fine. So for the numerator, what is the DF, and put on the colon, here goes DF, and this, okay, not F in the denominator, it's like DF like this, and between in the denominator. Okay, so between is equal to K minus 1. Okay, so yeah, hope I am clear with this particular thing. First of all, for the DFs of different groups, that what's the formula? So that is DF between first of all, and that is equal to K minus 1. Right, now next, coming to number 12, we have the equation for errors. Okay, so here we have equation for equation for errors within samples. Equation for errors within, and here goes the samples. So equation for errors within samples we are having, and that is basically the df's for the denominator. Df's for the, and here we have the denominator. Df's for the denominator. Denominator. Fine. So df's for the denominator we are having out here. So let me go down. So equation for errors within the samples, and we have then df's for the denominators. So into that we have just put on like this, and here I would mention out df, and that is for the within. Okay, numerator one was for the between, and for the denominator we have within, right? Putting on the equal to sign, and here we have n minus k. N minus k. Okay, yes, so that is again as well sorted out. Now let's go move forward and let's see regarding other ones. Now we'll be dealing with the mean square. One second. So right, so the mean square, that is the variance estimate as well, you could say, but I'm not gonna write that things. So simply goes a mean square explained by mean square explained by the different groups. So yes, this is the one, that is the mean squared explained by the different groups. Okay, now into that we have ms between. Downside goes the between, right? And that is equal to, let me just come down right here. So it's ms between, that is equal to, we have ss between and divided by df between. Right here, so like this we are having. So that's the mean square explained by the different groups. So for that we find out ms basically means the mean square, and between is basically the first category which we have. So for that the formula which we are having, it is ss between upon df between. Okay, now let's move towards number 14. So 14 we are having mean square, that is again I would say this is the variance estimate. So mean square I would write that is so it is due to, so mean square is basically due to chance. Okay, now into that we have ms, and here goes the within. So ms within, that is equal to, here we have ss within, divided by df within. Fine. So for here as well we are having out the mean square, that is basically due to chance, which is ms within is equal to ss within upon df within. Fine. Now ms and basically df can be written in one another way. I would show you. Ms between, sorry, the ms between and the ms within. Okay, the ms between and the ms within can be written basically in two ways. I will show you. Can be written as follows. Okay, so here for the first one, that is the A, we are having ms between, that is equal to ss between divided by df between. Okay, we have ss between divided by df between. Fine. And now that is equal to ss between divided by k minus 1. Okay, so yeah, right here we just put on the things like this. Let me just go down. For the next part, that's the B part, we have ms within. Okay, that is equal to ss within divided by df within. Okay, now that is equal to ss within divided by n minus of k. Right, so this one is as well written out here. Fine. So I would just now I would go over for a while. 1 second. So these were the calculation of the SS, that is my sum of squares, and MS, that is my mean of square. Let me quickly give you an idea. So K is basically equal to the number of different groups. Okay, Nj is equal to the size of the jth group. Sj is equal to the sum of the values in the jth group. N is equal to total number of all the values combined. X is equal to one value, and that is the sigma x is equal to sigma s of j. Fine. Next we are having sum of squares. Next we are having sum of squares of all values from every group combined. So that is sigma x square. Right. Then we have between group variability. So that is SS total. The formula we use is for the SS total sigma x square subtract minus, that is minus sign. Then on to the numerator we have sigma x whole square and divided by n, that n is in the denominator. Okay. Now next we are again having out okay, total sum of squares, that is again same, sigma x square minus sigma x whole square divided by n. Fine. Then we have the explained variation. So that is the sum of squares representing the variation among the different samples. So for that we have SS between is equal to sigma Sj of whole square divided by Nj minus, in the brackets we have sigma Sj of whole square divided by n. Right. Next we are having the unexplained variation. So that is the sum of squares representing the variation within samples due to chance. So that is SS within is equal to SS total minus SS between. Fine. Then we saw about the DFs for the different groups. So DFs for the numerator, that is the DF between is equal to K minus 1, right? Then we saw equation for errors within the sample. So DFs for the denominator, DF within is equal to N minus K. Then we basically have the mean square explained by different groups. So that is MS between, that is equal to SS between divided by DF between. Fine. Next we are having mean square, that is due to chance. So MS within is equal to SS within divided by DF within. So MS between and MS within can be written as follows. Okay, one second. Can be written as follows. That is MS between is equal to SS between divided by DF between, which is equal to SS between, you could even write out divided by K minus 1. That as well works. Okay. Now next we have MS within. So for MS within you have SS within divided by DF within, that is equal to SS within divided by N minus K. Right. So hope I made this particular thing very much clear to you regarding the calculation of sum of squares and the mean square. Now we'll be seeing some more things in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now let's discuss about some facts on which the one-way ANOVA depends out. Okay, let's discuss that out. So here I'm going to take out one color and let me start on with the writing. So for here we have the one-way ANOVA test dependent, where that basically on what are the factors, what are the things on which the one-way ANOVA test actually depends. So I would just start writing it from here. The one-way ANOVA test depends on the fact that MS between can be influenced by population differences among means of the several I would add on that here, among the means of the several groups. Fine. So basically the one-way ANOVA test which we have out, that depends on the fact that MS between can be influenced by population differences among means of the several groups. Right now, since the MS within, since MS within compares values of each group, since MS within compares values of each group to its own group mean, to its own group mean, comma, the fact to its own group mean the fact that, one second, let me get out some space. So since basically MS within compares the values of each group to its own group mean, the fact that group means, the fact that group means might not, sorry, the group means might be different, does not affect MS within. Fine. So, okay, let me just take on the cursor once right here. So what it actually defines out, that the one-way ANOVA test completely depends on the fact that MS between can be influenced by population differences among the means of the several groups. Since MS within compares the values of each group to its own group mean, the fact that group means might be different does not affect MS within. Fine. Next we have about the null hypothesis. Okay, what the null hypothesis says. So null hypothesis says that all groups are samples from populations, so here goes the populations. So null hypothesis says that all groups are samples from populations having the normal distribution. So here goes the distribution. Fine. So the null hypothesis says that all groups are samples from populations having the normal distribution. Fine. Now next what we are having, let me just close this out right here. Now what about the alternate hypothesis? So the alternate, let me just get down here so that I could write. So the alternate hypothesis says that at least two of the sample groups, at least two of the sample groups come from populations which have the I would just not write which have, I would write come from populations with different normal distributions. Okay. Now, what if the null hypothesis is true? So I would mention out that is as well, that if the null hypothesis is true, so in that case, so let me just come down, get out some space. So if the null hypothesis is true, in that case MS between M is between, and okay, here goes the S. M is between and M is alternate. Sorry, not alternate, that's the within, right? So M is between and the M is within should both estimate the same value. Estimate out the same value, right? So basically, one second, let me go above. Fine. So here it says that the null hypothesis says that all groups are samples from populations having the normal distribution. The alternate hypothesis says that at least two of the sample groups come from populations with different normal distributions. So if the null hypothesis is true, so M is between and M is within should both estimate out the same values, right? Now, after this, we have a quick note here as well to remember out. So I would just mention out that note as well. So it is basically, I would say it out. It says that if the null hypothesis, in null hypothesis, if all the group population means are equal. Okay, we can say that in null hypothesis, all the group population means are actually equal, right? So basically, the hypothesis of equal means implies that the populations have the same normal distribution. Because why? What's the reason that the population have the same normal distributions? As it is said that it is assumed that the populations are normal and they have equal variances. Right, so it is basically assumed that like the populations which we are having, these are having the similar variances, these are having the equal variances, right? So hope I made up this thing very much clear to you regarding that how we can go ahead and check on first of all the dependency of the one ANOVA test, and basically how we could say about the null hypothesis, fine? So here I'll be stopping, and now we'll see you in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So fine. Now today we are going to discuss regarding the F ratio or the F statistics, that what are these two terms and what do they actually mean out. Okay. So I would just put on the heading right here. The heading is F ratio. It's F ratio or it's F statistic. It's F ratio or it's basically the F statistic. Okay, now let me just come down right here. Let me remove out this particular one from this particular one. Great. Now what we'll be doing out here is that let's go ahead, proceed on, and let's see that basically what are the things that come under the F ratio or basically the F statistics. Okay, great. First of all, I will just let you know the formula. That's it's F is equal to MS between or divided by MS within. Fine. So F is equal to MS between divided by MS within, right? Now, I would just get down and get out some space for me of writing. So here we go, that if MS between and MS within, if MS between and MS within estimate the same value, estimate out the same value. Now, when can both of these have and estimate out the same value? When can this be done actually? So, it can be done in that particular case when we just, I could say that when we just say about that in that case when we believe that H0 is true. H0 basically means my null hypothesis. So, whenever my null hypothesis is true, so in that case I could say about the MS between and the MS within estimate out the same value, right? Then in that case what happens? So I could add on then the F ratio. Then the F ratio should be then the F ratio should be approximately. So in that particular case, the F ratio should be approximately equal to 1. Fine. So whenever the M is between and M is within estimate out the same value, so in that case the F ratio should be approximately equal to 1. Now, mostly just sampling errors, just sampling errors would contribute. Let me just go down here for a short time. Fine. So if the M is between and the M is within estimate the same value, then the F ratio should be approximately equal to 1. Mostly the sampling errors would contribute out. Okay, let me start writing out. Mostly these values will contribute the, and now basically here the variations contribute to the variations away from 1. Okay, just sampling errors would contribute to the variations away from 1. Okay, now in that case basically, now after that we have that when basically turns out to be the M is between, so it consists out of a population variance plus a variance that is produced from the differences which is between the samples. I would again repeat it. Let me write that only. So we have M is between, right? So M is between consists of the population variance plus a variance produced from the differences between the samples. Okay, this is what actually I was telling you in regard of the M is between. Now what if I talk about the M is within? So M is, and here goes within. So M is within. So M is within is an estimate. M is within is an estimate. Oh, okay. Let me remove it out. So M is within is an estimate of the population variance variance. Okay, it is an estimate of the population variance. So since the variances are always positive, so if the null hypothesis is false. Okay, M is within is an estimate of the population variance, right? So since the variances are always positive, if the null hypothesis is false, okay, so in that case M is between, what will I do? So in that case M is between will generally be larger. Let me come down. So in that case the M is between will generally be, here goes, will generally be larger than M is within. Okay, then in that case the F ratio that will be coming will as well be larger than 1. Okay, the F ratio that will be coming, it will as well be larger than 1 in that particular case. Fine. Now next we have basically if the population effect size is the most, okay, in that it is not unlikely. So we see that MS within will be larger in a given particular sample. Okay, if basically we are having some larger value or anything like that, so in that case we just take it out that the value for the MS within will be larger in a given sample. Okay, now what is the condition when these above calculations were done? Okay, so the above conditions were done with a group of different sizes. So different sizes were taken. What are the above calculations? So I have written out here. All these were performed. So basically, if the group size which has been taken, if that would be the same, okay, if the groups are basically of the same size, then the calculations basically simplify. Right, and the F ratio could be simply written out as, now in that particular case we have one more way to write out the F ratio when basically all the groups are having the same sample size. I would write that out. So I would mention that when groups have let me remove out, when groups have same sample size, so in that case we could say that for F ratio, then in that case the F ratio formula MULA formula. So when groups have same sample size, then the F ratio formula is, let me get out some space for me. So in that case the formula is capital F is equal to N into S. In the downside we have X bar whole square divided by S square, and here it's the pooled. Okay, so this is the formula which we follow when the groups are having the same sample size. Okay, now what are these parameters? So N is basically the sample size. N is the sample size first of all. Okay, then secondly we have DF numerator. DF numerator, what is that? That is equal to K minus 1. Then we have DF denominator. So DF, and here goes the denominator. Fine. What is that? That is equal to N minus of K. Fine. I would come down. Now next we are having S square pooled. S square pooled. Okay. That is equal to the mean. That is equal to the mean of the sample variance. Mean of the sample variance. Variance. Fine. Mean of the same sample. That's only the pooled variance which I have written above in the formula. Okay. Okay, that's not the variable. It's variance. Like this right here. The mean of the sample variance, that's called as the pooled variance. And next what I am having here Sx bar squared is equal to the variance of the sample means. The variance of the sample means, and here goes the means, right? So yeah, let me go above. Right, so this is about the F ratio or the F statistic. The formula is F is equal to MS between divided by MS within. Now if basically MS between and MS within estimate out the same value, then in that case the F ratio should be approximately equal to 1, right? Mostly the sampling errors would contribute to the variations away from 1. So MS between consists of the population variance plus a variance produced from the difference between the samples, right? Next, MS within is an estimate of the population variance. Since variances are always positive, so if the null hypothesis is false, so in that case MS between will generally be larger than MS within. When the groups have same sample size, the F ratio formula is F is equal to N into Sx bar squared divided by S squared pooled. What is N? N is the sample size. What's the DF numerator? That's K minus 1. DF denominator is equal to N minus K. Then we have S squared pooled. So that is equal to the mean of the sample variance. That is the pooled variance. And S bar squared. So X bar X squared are the variance of the sample means. Right. So hope I made this particular thing very much clear to you regarding the F ratio and right here. And the F statistics. Now we have some more things to look upon these things only, that I'll be covering in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now we are going to study about the notation of the F distributions, and we're going to study about some facts regarding the F distribution. Okay, so this is what we are going to study. So I would do out one thing. I would just take out a color here so that I could put on the heading. So here goes the heading. That's my notation for F, and here goes distribution. Okay, so distribution. Great. So here we have the notation for the F distribution. So we'll be seeing that how we denote out the and how we just put on the F distribution, what's the notation for that, like what symbols we use and all those things. Okay. So yeah, here what I'm going to do is I'm going to start up writing out here the notation for the F distribution. The notation for the F distribution is, what's the notation for the F distribution? That is F approximately equal to F. In the denominator we have df, that's the degree of freedom. Here we have numerator. Okay, numerator. Right here putting out a comma, and again we have degree of freedom, and next we are having here the denominator, denom. Fine. So this is how we are having out here the notation for the F distribution is F approximately equal to F df, and basically F df we have here the numerator, and for F df again, for that df again we have the denominator. Fine. Now what are these particular things all stands for? So let's start writing out here. So I would start writing out here that where df num, the degree of freedom, and the num is basically the numerator. Okay, degree of freedom numerator is equal to df, and here goes the between. Okay, and what about the denominator which we are having? Let me just get down here, and degree of freedom, that is df denom, denom, that is basically the denominator. So the degree of freedom denominator is equal to df within. Within is one another type. Remember we had deal with the between and within both, right? So in that similar case I have this df num, that is equal to df between, and df denom is equal to df within. Okay, now next we are having regarding the mean. So the mean for the F distribution, the mean for the F distribution is, now what's the mean for the F distribution? Let me get down here. The mean for the F distribution is mu is equal to d, we have here numerator, denominator, df. Okay, here the f as well, df numerator divided by df denom, that is basically the denominator, subtracted by 1. So this is the basically the formula for the mean for the F distribution. That's, again I would repeat it out, it's mu is equal to degree of freedom numerator divided by degree of freedom denominator minus 1. Now next we are having that what are the facts about the F distribution, right? What are the facts regarding the F distribution? So I'll put on the now heading again here. So that goes facts about the F distribution. So here goes the heading, facts about the F distribution. Fine. So I'm going to take out again one of the colors here so that I could proceed on with the writing. Great. So now we will be discussing about some facts about the F distribution. So it start out here. So the very first one is the curve, regarding the curve. Okay. So the curve is not symmetrical, but but is skewed. The curve is not symmetrical but is skewed to the right. To the right. So it means that the curve which we are having here for in the F distribution, that is not symmetrical but it is skewed towards the right. Okay. Moving forward, we have number 2, and that is there is a different curve. So there is a different curve. There is a different curve for each set of ds. That is, there is a different curve for each set of degrees of freedom. Okay. Coming down, we have the next point, that's the third point. Or you could even say that is the third fact, right? Whatever you just wish out. Fine. So for the number third, what we are having here? For the number third, we are having that the F statistic is greater than or equal to 0. So the F statistic is greater than or equal to 0. Okay, this is the next point. Next we have number 4 here. So next fact goes that as the degrees of freedom for the numerator I will just put on like this. Okay, so as the degrees of freedom for the numerator and for the denominator and for the denominator as denom like this. Okay, as the degrees of freedom for the numerator and for the denominator get larger, the curve, let me get down here. As the degrees of freedom for the num and for the numerator and for the denominator get larger, the curve approximates the normal. The curve approximates the normal. Fine. So as the degrees of freedom for the num and for the numerator and for the denominator get larger, the curve approximates out the normal, right? This is another fact regarding the facts about the F distribution. Fine. Now, what do we have? I would say we have a sort of graphs as well here, which helps us to display out some information right here as well. Okay. Now, as I mentioned about the skewness of the graph and everything, let me take the cursor in hand and I would, 1 second, right here. Okay, I told you that the curve is not symmetrical but skewed towards the right, right? That particular thing I mentioned to you. So it means that the curve which we are having, that is not symmetrical. The curve which we get out as an output, that's not at all symmetrical. Okay, it is basically skewed towards the right, as towards the right direction. It is skewed a little more. Okay, so for each and every set of different degrees of freedom, for each and every set of DFs, we have out a different curve. So as soon as the set of the degrees of freedom values change, and in that particular case as well, the shape of your curve will as well change out, right? So hope I am pretty much clear with all of these particularly things which I mentioned regarding here for this particular F distribution, right? Hope I am clear with the facts and even with the notation as well. So now we'll be meeting in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now we'll be discussing about a very new topic here, and that is test of two variances. So this is the topic that we are going to discuss now in this particular one. Okay. So I would just let me quickly take out a new color, then I would explain. regarding this particular function as well, that what it is, what are the things that are here, and how to use this throughout and all the things. Okay, right, here we go. Fine. Now, as I told about that, about the F distribution, right? We had discussed about the F distribution. So the another of the use, okay, another I could simply not use this. I would just write another use of F distribution. Another use of F distribution is testing two variances. Is testing two variances. Fine. So the another use of F distribution is basically testing of the two variances. Okay. Next, it is often desirable. I will just write out one example as well, so that it is often desirable to compare. It is often desirable to compare two variances. It goes like this: compare two variances rather than two averages. Okay, right? So rather than two averages. So here goes the averages, right? So the another use of the F distribution is basically the testing of two variances. It is often basically we just want to desirable that to compare two variances rather than comparing out the two averages, right? Now, next what we are having, fine. Now let's say for example, for instance, I would say that basically we have a college, and in that college administrators would basically like to we like to have two college professors, okay, that will be grading out the exams to have some variation in their grading. Right. So this is one of the things that actually sorts out our this particular test of two variances as well. So they are bringing other teachers from other particular college, so as to give out the grades to their college students. Right. Fine. This is the idea. Fine. Now, in order to perform out a F test of variances, what are the important things that needs to be kept in mind? So I would write that. So I would mention that in order to perform a F test, in order to perform a F test of two variances, it is important that the following are true. Fine. So in order to perform out a F test of two variances, it's completely important that the following conditions which I'm mentioning are true. Fine. So the very first condition that goes is the populations from which the two samples are drawn are normally distributed. So here goes the distributed. Fine. So the populations from which the two samples are drawn are normally distributed. This is the very first point that I was talking about, that it should be kept in mind, that all those things I'll be discussing, right? So that these should be true. This is the very first point that I had mentioned out. Moving towards the point number 2. So the point number 2, we have the two populations. Okay, one second. Yeah. So the two populations, LATIONS, the two populations are independent, are independent, let me get down here for a short while. So two populations are independent of each other, right? So the two populations which we are having, these are independent of each other. Fine. Now, basically, let me just go above for a short while and let me see what we have discussed. So we had discussed regarding the test of two variances, right? So we had seen the under use of F distribution is basically the testing of two variances. Fine. It is even basically often desirable to compare two variances rather than two averages, right? Now, one second. In order to perform a F-test of two variances, it is important that the following are the conditions which I mentioned. Those conditions shall be true. Okay, otherwise it won't work out like this. Alright. So what's the very first one that I'm having? The very first one that I'm having is the population from where the two samples are drawn are normally distributed. So the place from where the two samples are drawn, okay, those are the normally distributed. Next we are having that the two populations are independent of each other. Like both of the populations which you are having, both of them are independent to each other. Right? So hope I get out these ideas very much clear to you regarding the selection of all these things. And now we will be stopping up here only, and I'll meeting you in the next video with some more new topics. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So as in the previous video we had discussed regarding the test of two variances, that what is this test of two variances and basically what are the things we do and what we basically do not do, all of the things we have discussed out. Now let's quickly take out a very general example. I'm just not going to solve out anything or anything like that. It's a very general example that I'm going to take out, okay? So I would just simply change out a color, then I would proceed on with the writing. Great. Okay. So here goes that suppose we sample randomly from two independent normal populations, normal populations, fine. So suppose we sample randomly from two independent normal populations, okay. Now in that case what we are having, the things that we need to be put on here, I need to be remember out as well. Okay, dot. Fine. Now here we have let sigma 1 square and okay, and here we have sigma 2 square. So sigma 1 square and sigma 2 squares, these let be the population variances, and S1 square comma, okay, be the population variances and okay, this is S1. One second, let me write down 1 very clearly. 1. Okay, S1 square multiplied by, not multiply, here will go the and. Let me just get down here. So suppose we sample randomly from two independent normal populations. Let sigma 1 square and sigma 2 square be the population variances, and S1 and S2 squares be the sample variance fine. So one second, right here. So let these are sigma 1 square, sigma 2 square be the population variances, and S1 square and S2 square be the sample variance, right? So in that case, now basically what is gonna happen? Full stop. Let the sample sizes, so let the sample sizes be the population variances. Okay, let the sample sizes that I have already done that. Let the sample sizes be the, okay, not population, it's that another one, let be the N1 and N2. So N1 and N2 are basically the sample sizes which we have here. Okay, N1 and N2. Fine. Next, since we are interested, next is basically right here. Now, let's say we are interested in comparing the two sample variables we use for the F ratio. So in that particular case, yes, of course, we could use out this particular type of like you could use this particular type of question or answer this out in this particular way and address all of the things, right? Fine. So basically, as we just wanted to find out and we're interested in comparing the two sample variances. So in that case, we're going to use out the F ratio that's formula. Okay, let me just come down and show you that F ratio 1. So here it goes that F is equal to, then okay, now we are having S1 and S2. It goes S1 upon S2 whole square right here, okay, just like this. After that we have this, then we have the second one as well. Okay, so into that particular case I'll be mentioning out here S2. Okay, S2 in the bracket we have S2 square divided by and that is completely sigma 2, right? Sigma, okay, 1 second, and here it's sigma down wala na, right? So here sigma 2. Fine. So if this is the particular formula that we have out here, S1 upon, okay, that's S1 upon sigma 1 and S2 upon sigma 2. So let me now just clear out the complete formula and write that out again. So here we go on to the draw, and I will just run all of the things whatever we have written till now. Into that case, this draw comes here, and I will just put on the different things. Let's put on the formula first of all. Fine. So F is equal to, I have this one particular block, okay, and onto that particular block we have S1 square upon, okay, 1 second, S1 square and here we have V1 square upon, we have S2 square, okay, we have S2 square, and then down the line, down this particular one, we have sigma 2 whole square, right? So yes, this is how we just put on the things, we just put on the relevant formula. So after this, basically, what is this F having? So F has the distribution, here goes the F has the distribution, that is capital F approximately equal to, this is capital F, and into the bracket you have n1 minus 1 comma n2 minus 1, okay, where now into this case n1 minus 1 are the degrees are the, okay, let me remove that out, n minus 1 are the degrees of freedom okay, degrees of freedom for the numerator and n2 minus 1 numerator and n2 minus 1 are the degrees of freedom for are the degrees of freedom for the denominator, denominator. Fine, are the basic degrees of freedom for the denominator, right? So yeah, hope I am very much clear with all of those things whichever I have mentioned out. So let me give you again an idea. So we have taken on an example that suppose we sample randomly from two independent normal populations, right? Let sigma 1 square and sigma 2 squares be the population variances, and S1 square and S2 square be the sample variance. Let the sample sizes be N1 and N2. So F is equal to S1 square upon V1 square upon S2 square upon sigma 2 squared. Fine. So it has a distribution F belongs to F, that is in the afterwards, which is on the right hand side F. Inside that we have N1 minus 1 comma N2 minus 1 ke pure they have. Then we have N1 minus 1 are degrees of freedom for the numerator and N2 minus 1 are degrees of freedom for the denominator. Right, so hope I am very much clear with whatever I just referred regarding the F distribution. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So, as discussed in the previous video, we were seeing regarding a test of two variances, right? We had seen many random samples and all the things we had already seen for the two variances, right? Now basically I had even referred you the formula as well. Let me go back, and yeah, this was the formula as well that we have discussed out, right? Now, after this particular, we are going to discuss about some more things into this particular topic, right? Now, I have already told you about the n-1 and all those degrees, right? Now, I have some more important things to refer out here in a short while. So, yes, now we go ahead from here. So, now I'll be starting up here that if the null hypothesis, if the null hypothesis is sigma 1 squared is equal to sigma 2 squared, then then the FR ratio, that is the F ratio becomes, F is equal to, we have S1, okay, 1 second, I would just write that down, there so that it separates from the other and it doesn't mix up, okay. So if the null hypothesis is sigma 1 squared is equal to sigma 2 squared, then the F ratio becomes, we have F is equal to, from here we have S1 upon sigma 1, right? We have S1 up, okay, yeah, it is S1 squared, okay, and here we have sigma 1 squared. Fine, closing this out, dividing that by, here we have S2 squared, and okay, that's complete S2 squared, and it's complete sigma 2 squared like this, right? I'm closing out the bracket. Now that is equal to S1 whole square, okay, 1 second, I would remove this out. That is equal to S1 whole square divided by S2 whole square. Fine. So for the F ratio becomes, F is equal to S1 square upon sigma 1 square divided by S2 square upon sigma 2 square. Fine. That is equal to S1 square divided by S2 square. Fine. Now this is one of the more formula which we completely use out here. But here is one of the note that you shall keep in mind while using out this particular. So I am just going to mention out that particular note here. So note and putting on the colons, write this note. So here we have that the F ratio could be, okay, could also be actually, okay. The F ratio could also be, that is S2 whole square divided by S1 whole square. Fine. So it depends on HA, that is the alternate hypothesis, okay, and on which sample variance is larger, and on which sample okay, that is variance, VARI, and on which sample variance is larger. Fine. So it depends on HA, that is the alternate hypothesis, and on which the sample variance is larger. Fine. Right. Now, other than this, basically we are having some more things which are basically referred out here regarding some of the population and some others as well. So I'll mention them out. Let me get out some space here for writing, then I will proceed on. Fine, right here. So I would start that if the two populations have equal variances, INCES. Okay, if the two populations have equal variances, then S1 square and S2 square are, then S1 square and S2 square are close in value, and F is equal to S1 whole square divided by S2 whole square. Fine. So the two populations have equal variances, then S1 square and S2 square are close in value, and F is equal to S1 square divided by S2 square. Fine. Now, and it is basically close to the value, that is 1. So it is close to 1. Fine. But what happens if the two population variances are very different, putting out a comma here, comma, S1 square and S2 square tend to be very different. So if the basic total population variances are different, if the two population variances are different, then S1 and S1 square and S2 square as well tend to be very different from each other. Okay. Now, let's say I choose first of all the S1 square. So here goes our choosing S1 square as a larger sample choosing S1 square as larger sample variance as larger sample variance causes the ratio S1 whole square divided by S2 whole square. Fine. So choosing S1 square as larger sample variance causes the ratio S1 square divided by S2 square. Fine. And that to be greater than 1. Fine. Now, if S1 square and S2 square, if S1 square and S2 square are far apart means are basically far from each other, then, okay, 1 second, let me get out again some space for writing. Now, it goes that if S1 square and S2 squares are far apart, then in that particular case, we could say that F is equal to S1 square divided by S2 square. Fine. F is equal to S1 square divided by S2 square is a large number. Okay. Now, therefore, we see that it is close to 1. So I would just mention that here as well. Therefore, if F is close to 1, therefore if F is close to 1, so let me just get down out here. Therefore if F is close to 1, so in that case we say a little above, I just really want to go. Fine. Therefore if F is close to 1, so in that case the evidence favors the evidence, okay, FAVOR is that is the evidence favors the null hypothesis, the null thesis, right, the null hypothesis, fine. But if f is much larger than 1, then basically the evidence is against the null hypothesis. Then basically that is not in part of the hypothesis evidence, fine. So yeah, hope I am very much clear with all of these things which I mentioned up here regarding all. One second. Therefore, it's IE as well right here. Fine, so hope I am very much clear with all the things which I just mentioned out at this particular place regarding whatever we have studied for what are the conditions we had applied, and if basically the S1 is this and S2 is this, so what will happen and all those things. Hope I am very much clear with that, right? So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now let's take out a quick summary of this particular topic which we have studied, of all the small topics which we have studied under F distribution and one-way ANOVA. Right, let's quickly take out a quick revision here regarding all of those. So here we get started with the summary. So here we start out with the summary. Fine, let me just get down here, get out some space, and then I would start out. Fine. Okay. So what we studied about the one-way ANOVA. So a one-way ANOVA hypothesis, test, ANOVA hypothesis test determines if several population means are equal. If several population means are equal. So a one-way ANOVA hypothesis test determines that if several population means are equal. Fine. Now, the distribution for the test, so here we go with the distribution. So the distribution for the test is the distribution for the test is the F distribution, with two different degrees. Let me get out some space again. Okay, one way I will just repeat it out. That a one-way ANOVA hypothesis test determines if several population means are equal. The distribution for the test is the F distribution with two different degrees of freedom. Right? Now, what are the assumptions that we had made out here? So here goes the assumptions. So my very first assumption that we had made out was each population from which a sample is taken, is assumed to be normal. Fine. So each population from which a sample is taken is completely assumed to be normal here. Fine. Moving towards the next, that's number B point. Here we have the each sample is randomly selected. Each sample is randomly selected and independent. So here goes the independent. Fine. So okay, each sample is randomly selected and that sample is independent. After that, we have the third point. The third point says that the populations are assumed to, let me just go down right here. The populations are assumed to have equal standard deviations, equal standard deviations are assumed to have equal standard deviations, or basically we call that as variances as well, or variances. Okay, great. So this was about the one-way ANOVA. Now the next which we had was that a test of two variances, right? A test of two variances. So a test of two variances hypothesis test. One second, right here. A test of two variances hypothesis test determines if two variances are the same. Fine. So the test of two variances hypothesis test determines if two variances are the same. Let me let me put on a dot here. Fine. The distribution for the let me get down here. Fine. So the distribution for the hypothesis test is the F distribution. So distribution for the hypothesis test is the F distribution with two different so here goes a different with two different degrees of freedom. So degrees of freedom. So the distribution for the hypothesis test is the F distribution with two different degrees of freedom. Now what are the assumptions that we make out here? So here goes the assumptions. Let me get down here and let me start out some space and then write out. So the assumptions that we had made first was that the populations from which the two samples are drawn are normally distributed. Fine. So the populations from which the two samples are drawn are normally distributed. The second point we have out here is the two populations. So here we go with the populations. So the two populations are independent of each other. The two populations are independent of each other. Now let me just go above and give you again a quick summary of whatever we had studied in the summary for a one-way ANOVA and the F distribution. So a one-way ANOVA hypothesis test determines if several population means are equal. The distribution for the test is the F distribution with two different degrees of freedom. Assumptions are which we make out that each population from which a sample is taken is assumed to be normal. Second goes, each sample is randomly selected and independent. Third goes that the populations are assumed to have equal standard deviations, or we say them as variances as well. Now when we talk about the two variances hypothesis test, so a test of two variances hypothesis test determines if two variances are the same. The distribution for the hypothesis test is the F distribution which has two different degrees of freedom. The assumptions that we make out here is that the populations from which the two samples are drawn are normally distributed and the two populations are independent of each other. So whatever the summary I have referred here, in this particular summary, the assumptions are the ones which are really very important to be taken in mind. I would repeat that out. So each population from which a sample is taken is assumed to be normal. This one is for the one ANOVA test. Second one is the each sample is randomly selected and independent. And third one is that the populations are assumed to have equal standard deviations, or we call that as variances as well. Next assumption goes that the populations from which the two samples are drawn are normally distributed and the two populations are independent of each other, right? So hope I am very much clear with all of these particular points which I mentioned in regards of this particular summary of this F distribution and the one-way ANOVA topic. So here we complete up this new one more topic in the statistics for data science. That particular topic was F distribution and one-way ANOVA. So we have discussed many things regarding the F distributions and the one-way ANOVA. And we had seen many test cases, many formulas and all the things we have covered right here. Right, so I'll be stopping up here and next we'll be meeting with some new topics. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now from today we are going to start out a new topic, and that's a linear regression and correlation. Let me quickly put on some heading right here. After that I will be discussing regarding this portal, okay? Right here, so it goes that linear regression and correlation. Okay, this is a topic now that I am going to follow up here. So right here, this particular one, and now it goes. Now basically first of all I'll be starting up with a very introduction, that's what it is and what it is completely used for. So okay, see we have out a case here that professionals, basically sometimes professionals want to know that how two or more numeric values are related, right? Let's say you are having a numerical data or you are having some numerical sets. So into that case, sometimes professionals want to know that, okay, how are these numerical variables related, the numerical values, the variables which you are having, how are they completely related out, right? This is what they sometimes wanted to know. Example, let me take out. So basically there is a relationship between the grade on the second math exam a student takes. Okay, if there is basically if there is a relationship between the grade on the second math exam a student takes and the grade on the final exam, right? Is there a relationship? What does and how strong is the relationship? These are all the things which basically we need to know out. Let's say a student had given out the second math exam and a student takes out the grade, and basically what's the grade on the final exam as well. So this is what basically it's willing to know for basically wanted to know, right? Another example, I could say that your income may be determined by your education, your profession, your years of experience and your ability, right? So the amount you pay a repair person for labor is often determined by an initial amount plus an hourly fee. Right? These are all the examples in which where can the regressions be used out, right? So basically here these are the cases where the regression can be used. Also in that case, the type of data described in the examples, right, the examples which I had given you right above. So type of data which I had described there was the bivariate. Data. We often call it as BI. Okay, we often call it as BI. So bivariate data, we often call it as BI. Okay, that's BI for the two variables. Bi means the two variables, right? So it's for the two variables only. So in reality, basically, statisticians mostly focus upon the multivariate data. So it's multivariate, and here goes the data. Fine. So the examples which I had shown you, that for the bivariate data, bi means the two, right? And basically the statisticians completely see about the multivariate data. Okay, that means having the many variables, right? So This particular linear regression and correlation topic focuses upon the studying of the simplest forms of the regressions, right? Like the linear regression with one independent variables. We'll be seeing about the data that fits in a line in 2 dimensions. We'll study about the correlation. That what is this correlation for? It basically measures that how strong the relationship is, right? So these are all the things that we will be studying up here in this particular topic, that's a linear regression and the correlation, right? Now what I'll be doing is that I'll be taking you to the very first topic that not like this, I'll be taking you to the very first topic that I am having right here, and that's the linear equations. Okay, yes, this is the topic. Okay, let's come down and start studying about this particular thing. So I would start with the writing only that linear regressions, the linear regression for two variables, the linear regression for two variables is based, linear regression for the two variables is based on a linear equation, is based on a linear equation. It's based on linear equation with one independent variable. Okay, now the form which we are having here in the for linear equations form that we have out here, so it's y is equal to a plus bx. Y is equal to a plus bx. Hope many of you are familiar with this particular form as well. That's y is equal to a plus bx, because we get out these things in our very younger classes, right? We have already studied about these things onto our younger classes, right? So this is about linear equations, that linear regressions for the two variables. It's okay. Okay, how come this particular has been appeared? Let me quickly remove this out. Till the time I would not speak out, I would not deny while speaking out. Okay, yeah. So linear regressions basically it's for the two variables, right? We had already seen out the formula as well right here. That how is the formula and how is that completely applied out? Okay, 1 second, right, and fine. Now let me just come down here, get out some space for me to write out, and write here. Okay, now I will be seeing about some more things. Okay, where what are the values of a and b which I'm having here. So I could just simply write out here that where a and b are constant numbers. Okay, where a and b are the constant numbers, right? The constant numbers which we are having. So that is the a and b. Okay, now I could mention out here that x is the independent variable, and y is the dependent variable, right? So basically we could mention out here that x is the independent variable and y is the dependent variable, right? So basically what we do, we basically choose out that which value we need to substitute for the independent variable, and then basically we solve out the dependent variable things and things related to dependent variables, right? So in that similar case, I just mentioned out here that x is the independent variable and what's the y is the dependent variable which we are having out here, right? So when we talk about the linear regression or correlation, so in that case two terms come. That first one is the bivariate data, that is bi, and the second one is the multivariate data, that's basically for the multiple variables. Now when we talk about the linear equations, so in that case the linear regressions for two variables is based upon a linear equation, okay, which has on a linear equation. That particular linear equation shall have about one independent variable, right? Y is equal to a plus dx, and where a and b are basically the constant numbers which we are having here. Okay, what about x? So x is the independent variable and b, c, and y is the dependent variable which we are having. So it completely depends that what variable you set on as dependent and what variable you set as independent. That depends on you, right? So you completely to choose out a value to substitute for the independent variable and then solve out the dependent variable. Okay, hope I am very much clear with this particular thing to you as well, right? Now what I'll be doing is that, so here I'll be stopping up this particular video and we'll be meeting you in a new video with some new things regarding this linear regression, the correlation. Basically we'll be continuing it, right? So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now I'll be discussing about the summary of all the formulas which we had seen into this relevant in this particular topic, that was the chi-square distribution, right? So here now we go with the summary of all the formulas. So here it's my topic, summary of, and here goes the formulas, right? Yeah. This is what we are gonna study right today, and we're gonna take out a quick summary of the formulas so that at the time of revision and all these things, these particular quick summaries help us a lot while dealing with the questions and while dealing with all of the things, right? Okay, so I'll be starting up here with the quick summary. So what I'll be doing is that I would quickly take out a new color from this particular place. Let's say it's this one, right here. So let's start out. So for the first thing, I'm just quickly going to discuss about the chi-square probability distribution. So the chi-square probability, the chi-square probability distribution, right? So for that, we are having the formula that's mu is equal to df, and we are having the formula that sigma is equal to under root of 2.df, right? These are the formulas that we are having out here for this particular probability distribution. Now let's move towards the topic, and that's the goodness of fit hypothesis test, right? Let me come down, get out some space for writing. Putting out a dot here, and yes, from here it starts out that it is goodness of fit hypothesis test. Okay, this is a topic, that's a goodness of fit hypothesis test, right? So the very first point goes here that use goodness of fit. Okay, instead of writing out the complete name, I would simply write or use this. Okay, use this test to find, whether a data set fits a particular probability, distribution. Probability, and here goes the distribution. Okay, right. So this is what this particular goodness of fit hypothesis is used for. It's basically used for checking out this particular to find that whether a data set fits a particular probability distribution or not. This is what it is used for, right? So yeah. Okay, I will just make out a little bit of change here. Just let me quickly open out remove out this notification thing. 1 second. Yeah, right, here it goes. Okay, so yeah, goodness of fit hypothesis test. So in this test, basically use the test to find whether a data set fits out a particular probability distribution or not, right? This is what it is used for. Next, what we are having out here. So the second point, we are having the degrees of freedom. Let me come down here. That the degrees of freedom are number. So the degrees of freedom are number of cells or categories. Are number of cells or categories minus 1. Right? This is what the degrees of freedom are. So degrees of freedom are number of cells or categories minus 1. Fine. Next we are having the third point. Now what we are having here. So the test statistic is, what's the test statistic that we are having? So it's the, we have already seen sigma, downside we were having k, above we were having O minus E whole square divided by E, right? This is what we were having as a test statistics. So test statistics is this, putting out a comma and using out here that where O is equal to, we have the observed, O is equal to observed, then we are having here values. Into the bracket, we will just put on the data, that's the data as well, right? So yeah. So this is about where O is equal to observed values and the data. And what about E? What we were having as a E? So E was my expected values. So here goes expected and here goes the values, right? And that's from the theory. So from, and here goes theory. Fine. So O is basically my observed values and E is basically my expected value, right? What about the K? We were having the K as well, right, into the formula. So K is the, it's the number of different data cells or categories, right? So K is basically the number of different data sets or the categories which we have out. Okay, fine. Coming down here, next we are having the point number 4, and the point number 4 is that the test is right tailed. The test is the right tailed, right? So yeah. These are some rules, these are some, you could say, a summary, a quick recap regarding the goodness of fit hypothesis test, right? Hope I am very much clear with this particular. Next, I'll be moving forward with the test of independence, right? So here put the point, and here goes the test of independence. Okay, right here. So what I'm gonna first point which I have, that they use the test of independence. Use the test of independence. Use the test of independence to test whether two factors. To test whether two factors are independent or not. Are independent or not, right? So first of all, the test of independence is used to basically use the test for independence to test out that whether the two factors which are like they are independent or not. Right now, next point which we are having, the degrees of freedom. So here goes the degrees of freedom. So the degrees of freedom are equal to let me come down. So degrees of freedom are equal to, what are these equal to? These are equal to number of columns minus 1 into number of rows minus 1. So here goes number of columns minus 1, and next we are having number of rows minus 1, right? So yeah, this is the degrees of freedom, and that is equal to both of these particular things. Fine. Now moving next, we have the test statistic. The test statistic which we have for this is, so the test statistic is, we have here the sigma, here goes I multiplied by j in the bracket, and next I'm having O minus E whole square divided by E. Okay, The test statistics is this, okay? Where, now what are these all notations which I had put on? So I would just write on where O is equal to, it's the observed value. O is the observed value. Fine. What about E? So E is basically the expected value. It's the expected value. Okay. And what about the I and the J? So I is, okay, let me write it out. I is equal to the number of rows. Okay, number of rows in that table. So it's not, I do not think so to write out the that as the number of rows in the table. Okay. And what about the J? So J is basically the number of columns that we are having. So it's the number of columns. Right. So yeah, this is the formula regarding the test of independence for all of these particular things. Right. Now what I'll be having next is that, let me just go down quickly a little bit here. Now, what next thing regarding this particular, okay, it's the fourth point. So, this particular test, the test which we are seeing, that is the test of independence. So, the test is with the right-tailed. It's right-tailed. Okay. And next regarding the last point, that if the null hypothesis is true, then basically the expected number, the expected number which we have, that is, if the null hypothesis is true, then the expected number, that was E, right? So that E is equal to row total, in the bracket we were having column total, row total, column total, and downside we have the total surveyed. So total and surveyed, right? This is what we have right out here. So if the null hypothesis is true, so in that case the expected number, that's the capital E, that was we have used in the formula as well. So capital E was denoting out the expected number, right? So it's row total into column total upon total surveyed. Right, so hope I am very much clear with this particular thing as well regarding the test of independence. Right, so here we had taken the summary regarding the test independence and what was the above one that we had seen. So that was goodness of fit hypothesis test. Now we are left with two of the things, test of homogeneity, and the next which we are left out here with is the test of the single variance. So that we'll be seeing up in the next video. So this is all for this video. Till then, thank you and take care. Hey everyone, my name is Shambhavi. Hope you all are doing well. So, so far slowly we have came to the end of the statistics. So, I just wanted to let you know now that further after studying up of all the topics up in detail and rest everything pretty much clear. Now just wanted to let you know that what's the correct way for approaching up a statistical analysis problem, like how you should approach for solving up a statistical analysis problem in the step-by-step format. Okay, so we'll be learning about the approach for solving. I could write a statistical approach for solving statistical problems. Okay, so this could be the respective topic which we are going to discuss about today. Okay, so let me start up with the things for now. So let me just get down here, and I could take up a color from there and we can just proceed on with the writing. Pretty clear. Okay, so statistical analysis statistical analysis means investigating. Okay, yeah, so statistical analysis means investigating trends, patterns and relationships using quantitative data. Okay, using quantitative data. Okay, this is what is meant by the statistical analysis. A statistical analysis means investigating the trends, patterns and the relationships using the quantitative data. Okay, now pretty fine. It is important, let me start writing it out here, that it is an important research tool. It is an important research tool used by scientists, okay, used by scientists, governments, businesses, and other organizations okay. So this is what a statistical analysis actually means. So the statistical analysis means investigating the trends, patterns and relationships using the quantitative data. It is an important research tool which is used by the scientists, government, business and other organizations. Okay. Now, further, to draw valid conclusions, statistical analysis, so to draw valid conclusions, the statistical analysis requires a careful planning from the very start of research process. Okay, so for drawing up the valid conclusions, the statistical analysis requires of the careful planning from the very start of the research processes. Okay, so there you need to specify your hypothesis, and make decisions. DECISIONS. You need to specify your hypothesis and make decisions about your research design, sample size, and sampling procedure. Pretty fine. So for drawing up the valid conclusions, the statistical analysis requires the careful planning from the very start of research process. Okay, so into that you need to specify your hypothesis and make the decisions about your research design, about your sample size and the sampling procedure. Okay, then next what do you do? Then next after that, right here, after collecting data, after collecting data from your sample, you can organize and summarize the data using the descriptive statistics. Okay, using the descriptive statistics. So after collecting the data from your sample, you can organize and summarize that respective data with the use of the descriptive statistics. Okay, then further what to do? Then you can use the inferential statistics, then you can use the, one second, let me just get down. Then you can use the inferential statistics to formally test hypothesis, and make the estimates. Okay, and make the estimates. So then you can use that inferential statistics to formally test up the hypothesis and make the estimates about the populations. Okay, and finally, then next goes that finally you can interpret and generalize your findings. Pretty fine. Now, okay, one second, let me read the cursor. So further, after collecting the data from your sample, what you can do, you can organize and actually summarize the data using the descriptive statistics. Then you can use that inferential statistics to formally test the hypothesis and make the estimates about the population. Then finally, you can interpret and generalize your findings. This is what is the approach for solving up the statistical problems. Now, okay, let me just give you a quick review whatever we just discussed it up here, and further I have some more things. So statistical analysis means the investigating the trends, the patterns and relationships among the quantitative data with the help of the quantitative data, right? So that's an important research tool which is used by the scientists, the governments, the businesses and many other organizations. So to draw up the valid conclusions, the statistical analysis requires the careful planning from the very start of research process. Okay, so you need to specify your hypothesis and make up the decisions according to your research design, the sample size and the sampling procedure. After collecting the data from your sample, you can organize and summarize the data using descriptive statistics. Then you can use the inferential statistics to formally test the hypothesis and make estimates about the population. Finally, you interpret and generalize your findings. This is what is the procedure, the approach for solving up the statistical problems. Okay, right here I discussed about this approach in a little bit of, you could say, in a little bit of paragraph manner. I just wrote everything in a paragraph. Further, in the next video, I'll be discussing this approach in the steps format, that step by step how to approach up the thing, so that it will be very much easier for you to follow up that respective approach, right? So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So, into the last video, we discussed about the approach for solving up the statistical problems, right? So, we discussed up this respective approach. Now, today in this particular video, I'll be taking you through the stepwise procedure for solving up the statistical problems, okay? So let me get down this recap of the previous video I would give in the last, not right here. Okay, so let me just quickly take up a new color here, and okay, let's do this with this one, and now let me proceed on with the writings. Okay, so my very step, the step 1 of mine goes up like this. That first of all, what do you have to do for approaching up a statistical problem? You have to write your hypothesis, and plan your research design. The very first thing that you have to do. So you have to write up your hypothesis and plan your research design into that respective case. Okay, the very first step that you have to follow. Now in this writing up the statistical hypothesis, into that you have the null hypothesis, the alternate hypothesis, everything you're having there, right? So the very first approach will be, you have to do that all of the hypothesis, and you have to simply plan up your research design. Now the second step which goes up here is that you have to collect up data. You have to collect up the data from a sample. Okay, from a sample you have to collect up the data, and onto that respective data only. Further you have to proceed on with the different things, like you have to do the sampling of that data for performing up the statistical things, and all those things could be done up here at this respective place for your respective data, whatever you have collected, like from a sample, right? Now, how to do up the sampling and all those respective things that I did already have covered up into my previous videos of the statistics for data science. So you can just go out and watch out those videos. So if you do not know about the sampling, if you want to know about the hypothesis testing and all those quiz and all the alternate, the hypothesis testing and rest everything. So yeah, again you could go on to my previous videos and have a look, because yes, I did already covered up that things into my previous videos. Okay, great. Further, after my step 2, I have my step number 3. So my step 3 goes up in such a manner that in the step 3 I have to summarize. In the step 3 I have to summarize your data. In, let me just get down and get out some space. So summarize your data in descriptive statistics. In descriptive statistics. Okay, what does this come in the descriptive statistics? Like inspecting your data, like organizing your data onto the frequency distribution tables, right? Displaying the data from the key variables in the bar chart, making up the scatter plot. So this is how you will be summarizing up your data in the descriptive statistics. Okay, so in statistics we have descriptive and inferential 2 times. So for the descriptive you have to go ahead with the step number 3. So like when you have collected up your data, and when you have actually collected up all of your data, so you inspect them, and you calculate out the descriptive statistics, and that summarizes your complete data. So yes, the same procedure has to be followed up here. You have to summarize up your data into the descriptive statistics. Fine. Then your go is the step number 4. Okay, now what is the step number 4? So into that, your step number 4 goes that you have to test the hypothesis, or make estimates, with inferential statistics. So into the step number 4, you have to test the hypothesis, or you have to make up the estimates with the inferential statistics. So into that, the estimation and the hypothesis things will come and help you about. Okay, so like what are the different estimations, like point estimation, interval estimation, all of those things will come up here. You have to apply up all of those respective things. You have to apply up all of those respective rules, and then further you have to do up the hypothesis, or you have to make up the estimates with the inferential statistics. So in the step number 3, there came the use for the descriptive statistics, right? In the step number 3, you did use about the descriptive statistics, and here up in the step number 4, you have to use up the inferential statistics. So it's not that case that one type of statistics is used and the other one is not used. No. First of all, this descriptive has been used, and then comes the use for your inferential statistics. Okay. And now further going up with the step number 5, you have to interpret your results. Okay, so now on to the step number 5, you have to interpret your results, that how are your results, like the statistical significance of your results, and what are the results that you have achieved after this hypothesis and after all of those respective steps. That has to be mentioned up by you, right? So into that, now what do you have to you have to compare up the different types of values. Statistically, you have to make up some significant results that will help you to get and interpret your final results. Okay, so these are the 5 steps that you have to use up here for approaching up the any kind of a statistical analysis problems. Now if you're not clear with any of the type of thing here, any type of a step, that what is this and how to approach, what are the topics and how do I learn the topics. So what are the approaches I did have mentioned up here, for all of these things I already have up a lot of videos onto my respective playlist for Statistics for Data Science. So there you could go ahead and simply follow up any other respective topic which you want to learn among all of these steps. So first of all, you have to write up your hypothesis and you have to plan about your research design, right? The very first step that you have to do. Then you have to collect some data from a sample. Whatever the sample you are having, from that you whatever data you are having, collect up some sample from that data. Then you have to summarize up your data in using the descriptive statistics. So with the help of the descriptive statistics, you will be summarizing up your data. Further, on the step number 4, you have to test up the hypothesis, or you have to make up the estimates with the inferential statistics. Now, after summarizing your data in the with the help of descriptive statistics, you will be testing the hypothesis, or you will be making up the estimates with the inferential statistics. And further, with the step number 5, you have to interpret your results, whatever are achieved. Right? So now, if I talk about this thing, whatever we just did, long way, so I could tell you that. So first of all, statistical analysis actually means about the investigation of the trends, the patterns and the relationships with the help of the quantitative data. So it is an important research tool which is used by the scientists, by the governments, by the businesses and many other organizations. Now for drawing up some valid conclusions, the statistical analysis requires the careful planning from the very start of the research process. In that, you need to specify your hypothesis and make the decisions about your research design, about your sample size and about the sampling procedure. After collecting data from your sample, you can organize and summarize the data using the descriptive statistics. Okay. Then you have to use up that inferential statistics for formally testing the hypothesis and making the estimates about the population. And then finally, you can interpret and generalize your findings completely, right? So this is the actually a theoretical approach and a step-by-step approach for solving of the statistical problems, whatever you get further. So now here we finish up the statistics for data science. From my side, I covered each and every topic, whatever is required, whatever is not required. I just gave you the knowledge for each and every respective topic into this. So the complete playlist has been now updated, and from there you could just go ahead and you could start learning your statistics for data science. For the next, I'll be coming up with the now probability. Okay, so statistics we did have covered. Now the next one will come up the probability. So now we'll be covering about the probability for the probability for the data science. Right, so I hope that you have enjoyed learning the statistics for data science. So if you did enjoy learning, then please come go ahead and subscribe to my channel and then follow me for the probability for data science as well. Right, so from next like video for the statistics, we'll be doing up the probability. Right, so this is all for this video. Till then, thank you and take care.